about building an airplane with a wing. So that's what we're going to do next. So these are possible configurations. So first option is just do a wing. So case number one, let's say we pick a 0 camber airfoil. So here's our airfoil. There's the aerodynamic center. There's no pitching moment. When it's a symmetrical airfoil, there's no pitching moment. So all we have is lift. So let's talk about, well, where do we put the center of gravity? We have the center of gravity here. Then the lift produces a negative pitching moment. For trim, we want the pitching moment to be 0. So that doesn't work. So with this position, CM, or the pitching moment, is not 0. We do get stability, because if the lift increases due to a gust, it's going to nose down and reduce that alpha back. But we can't trim, so there's no trim. So if you look at it, in order to be able to trim, we're going to have to march the CG back. So we could put the CG here, and then we can trim. Does the blue show up? That's not bad. But then the stability is 0. If we get an increase in angle of attack, the lift increases, but since the lift is acting at that same point of the CG, we get no change in the pitching moment. So it's neutrally stable. So that's not a good option. So let's try a different airfoil. So that was symmetrical. Let's try a positive cambered airfoil. This is option 2, a cambered airfoil. There's the aerodynamic center. The lift is acting at that. And with a cambered airfoil, you get the pitching moment negative. So I drew it in a negative direction, down like that. So let's look at different CG positions. We could have the CG here. So what do we get there? Looks like the lift is nose down, and the pure couple, CM or M, is nose down. So we get a negative pitching moment, so there's no trim. So that's not good. We do have, it looks like stability, because if we get a gust, we get an increase in lift due to the gust. It's going to nose back down to cancel out the alpha increase. So we do have stability. So the other option, it looks like in order to get trim to happen, we'd have to put the CG back here so that the lift generates a moment up, and CMAC, the aerodynamic, the pitching moment, is negative. And if we balance this distance just right for a certain flight condition, we could get trim. So we could have the total pitching moment 0. But now if we get that gust happening, increase in lift, that's going to create a nose up. And so it's unstable. So we can trim this thing, but we can't make it stable. And if you put the CG right at the aerodynamic center like we did with the other case, then you can't trim it because you've got the pure coupled down and nothing to balance it out going up the other way. All right, we're just going through options here to see why airplanes are built like they are. All right, so how about a negatively cambered airfoil? In other words, we're going to flip it upside down. So we flip it around. If we tilt it enough, we're going to get lift up, and it's going to flip the pitching moment. So here's what we've got now. Got an airfoil that looks like that. Here's the aerodynamic center. And if we tilt it up enough, we can get lift like that. And we've got a positive pitching moment just because of the pressure distribution of this thing. And so if we put the CG here, we can get trim. We can get pitching moment 0 because the lift times this moment arm gives us a nose down, and the pure couple gives us a nose up. So we get that. How about stability? An increase in lift due to an increase in angle of attack, the thing pitches up. It's going to tend to nose down, and so we get good stability. So that works, but an airfoil cambered like that has bad drag characteristics. Just it produces lift, but you have to tilt it up a lot to get lift, and so you get a lot of drag. So you could do this. It just doesn't always work that great. Any questions on what we're doing so far? Somebody's asking what AC is. That's aerodynamic center. CM, subscript there is CM alpha. That's pitch stability. Okay, so wing alone is a tough option. So let's try something else. So this is option B. Wing plus tail. Well, that sounds like how airplanes are built, so why did they do that? So here we've got option 1. Here's the wing. We've got the lift of the wing And notice I've done a positive cantilevered airfoil because they're aerodynamically efficient. We get a negative pitching moment from that thing. And then we're going to stick a tail back here. And we'll make the tail symmetrical so that we don't get any pitching moment. So there's a symmetrical tail. So we just get lift of the tail. And then we have to say, well, where do we put the CG? So looking at this thing, the lift of the wing is going to be that way, and we get a CMAC. So we get a nose down couple from the lift distribution. So if we put the CG here at just the right spot, the nose up of the lift can cancel out the nose down due to this pure couple. Okay, so that's good. And so the lift of the tail can be pretty small. But if we put the tail far enough back, when we get a gust, this lift goes up and this one increases. It may be really small, but then we get a significant a change in the lift here. And if you put the CG and the tail far enough back, this creates enough of a nose down to counteract the nose up here, and you get stability as well. And what really matters is where is the net resultant of the lift, right? We've got to make this big enough and far enough back that the net resultant of the lift, the total lift, add the lift of the wing and the lift of the tail, that when these deltas happen, you get it acting behind the CG, and that's what gives you the stability. And in fact, we'll have to find this point here. It's called the neutral point. We'll define that more precisely later on. But we want to make sure that that's behind the CG so that we do get that stability behavior. And it's the wing relative to the size of the tail and how far back the tail is, right? Because in a distributed load, you're finding the resultant of these two lifts. It's going to, this point is going to be determined by how big that is and how far back it is. So with this case, you can get trim, and you can get pitch stability. In other words, a change in pitching moment with change in angle of attack is negative. So when alpha increases, you get a nose down or a negative pitching moment that counteracts it. All right, another configuration that's not used as much, but you do see, is where you put the horizontal tail in the front. That's called a canard. In fact, that was the way the Wright brothers built their airplane. So another option here. Yeah. Okay, yeah, I didn't see it pop up. Tail to be in plane with the wing. I don't understand what in plane means. The same level up and down? Yeah. It doesn't matter. I mean, there are airplanes that have a T-tail where it's up here. You don't see very many with it down here because it hits the ground when you land. Looks like some other people were answering. NP, neutral point, that's what I said. And again, we'll define that. Oh, somebody answered. What does TY mean? Gotcha. Thank you for answering that. Okay, Canard, thanks for a heads up. When you see those things flash up there, I'll stop and answer questions. All right, and then option 2 for the wing plus the tail is what's called a canard. And that's just a name for the configuration where the horizontal tail is in front rather than in the back. And it's pretty much the same balancing act that we've been talking about. There's the wing. Here's the aerodynamic center. You have a negative pitching moment. And then you have a tail up here called a canard with its own lift. And so the secret here is you've got to pick a position for the CG where you can trim. And obviously you can do that because this nose down pitching moment can be balanced by a nose up pitching moment from the canard. Oh, and by the way, when we were talking about trimming with the tail in the back, obviously you can adjust the lift of the tail in the back to balance things out as well. So that additional adjustable parameter helps you out. Oh, it's negative, yeah. Typically, they're both cambered. I mean, you can make it symmetrical, so there's none there. It's your... Well, yeah, so this, remember, comes from the pressure distribution, the distributed load, where you get a pure couple, and then you get the net force as well. And that's the stuff you do in statics with the distributed loads. And so the secret here is to choose the CG so that that net resultant of this lift and this lift acts behind the CG. And this is trickier than the horizontal tail. The horizontal tail, you just stick a tail really far back there and make it big enough. Here, you've got to balance the locations in the CG pretty carefully to get the stability here. So that when you get the gust and you get the delta lift, you get the nose down pitching moment. But it can be done. And one of the advantages that they talk about here is that very often the wing and the tail both produce positive lift for all of the flight conditions. With the horizontal tail, sometimes the horizontal tail is producing uplift and sometimes it's producing downlift. And that downlift takes away from the lift of the wing. So there's some efficiency there. And there's also some efficiency of the wing and the wake from the wing hitting, I mean, the wake of the canard hitting the wing that has some positive or negative aerodynamic effects on the wing. You have to do it right. One of the, pardon? Okay, let me say one more thing and then. One of the advantages of this is when you're talking about stall of the airplane is you can design the canard to stall first before the wing, so you tilt it up a little bit more. And if this stalls, then it's going to unload the canard and it's going to pitch down and unstall the aircraft. So it's kind of stall proof. Whereas with a conventional wing and a horizontal tail, if the wing stalls, you have to be careful with to stall the root on the tips, the root instead of the tips, and there's some other characteristics of that. But this does help out with stall because this will stall and then it'll drop you back out of stall pretty quick, carefully. Yeah, what was the question? Yeah, the horizontal tail, we'll add an elevator later on. You can either adjust the horizontal tail by moving it completely, or you can put an elevator on it that gives you the up or the down lift. And you do the same thing with a canard. You could put an elevator on a canard here and adjust the lift of the canard to balance things out as well. I don't know about the comment about turning without the elevator because the elevator doesn't turn. Yeah. Yeah, the ailerons bank the aircraft. Now, when you go into a turn and you start pulling G's, you have to add some aileron to keep you in the turn to pull the G's, but that's a different story. Oh, I talk about the vertical stabilizer. Yeah, don't worry. Ask questions. We'll figure it out. Yeah.
So you essentially said that most, that most only aircraft configurations were like useless or didn't work. Do you know how, for example, the B2?
That's the next thing we're going to talk about.
Okay.
So there's several ways you can deal with that. One way, and that's what the B2 does, is it's not aerodynamically stable in pitch. They have a computer on board that senses the pitch angle and reflects the trailing edge surfaces in order, if the airplane pitches up, its natural tendency is going to be unstable and pitch up more, but it actively goes back to those surfaces and causes it to pitch down. And so that's an active output feedback control system. So that's one way to do it if you have enough money, and that all you care about in that is that it's stealth. So there's a lot of trade-offs done in that design to get the stealth. The other way you can do a flying wing is you can sweep it back. So if you have a flying wing like this, we said, well, we need a tail, right? Well, you can just take, because the tips of the wings are swept back, you can take the tips of the wings and you can twist them to give you the pitching moment to balance out. Or you can put control surfaces, essentially an elevator. I've kind of drawn a weird wing here. But you can adjust those, like the elevator on the tail, to get the pitching up or pitching down that you need. Yeah. There's what? What did it say? The neutral point for what? Yeah, we'll define, the neutral point is the resultant, the point where the resultant lift of the tail and the wing act. Right, you have two force vectors. The net resultant, if they're both equal, will act here, right? So the neutral point is just the net, the point where the net lift from both the wing and the tail act. But it will become very important because we will need to calculate where that is to make sure it's behind the CG to get the stability. All right, what's next? Any questions here? You guys, you'll raise your hand, right? So did this make sense? Either you put an active control system, which you'll learn about in AE514, or you twist the wings to get trim, or you put flying control surfaces on there where the pilot can control it with those as well. Flying wing is much harder to deal with, and it's not as aerodynamically efficient. That's why you don't see them very often. How are we doing on time? 11:01. All right, so we've talked through the general idea of the wing pitching moment, the tail pitching moment, how you calculate the trim and the stability. So now we want to go into the details of that. If you're building an airplane and you've developed a wing, like we've already done, you can predict the lift of the wing and the pitching moment. So let's calculate the total pitching moment of the wing, the total lift of the wing, add in the tail, and then we'll build an airplane. Because the goal, again, is to have the total pitching moment for pitch trim to be 0, and the change in that moment with respect to angle of attack to be negative. So we need to get both of those. All right, so I want you to draw this picture with me. We're going to draw the wing. We're going to calculate the wing pitching moment. And along the way, we're going to define some terms and letters and dimensions on this diagram that we need to talk about, well, where's the wing located and things like that. Okay, the first thing you're going to do, and we're going to need a lot of room for this. So actually, let's go over to the cleaner board. I'm going to start at the top, draw the average chord of the wing. So this is C bar. So dimension this way, we're going to need more room. So that is the mean aerodynamic chord. That's the average, the area weighted average chord, the thing that we calculated for our straight taper wing and everything else. If you really want to, you can draw an airfoil shape in here that represents that average. But remember that the wing itself, especially if it's one of these tapered wings that's not rectangular, they'll have different airfoils all throughout there. And what we're doing is we're just saying we're going to pick this one part that's the mean chord, and that's what we're going to use to represent our airplane. And we have an aerodynamic center on there where the total net lift of the entire wing acts. That's the resultant of the distributed load over the wingspan. So, but step one, draw C bar and then dimension it like that. So that's step one. Everybody got that? Okay, step two, draw the aerodynamic center of the wing. So that's the thing that we calculate X bar, Y bar, Z bar. So to get that point, we need to know X bar, because that's the distance back to where that thing is located. Okay, so far so good. And we're going to label that. Here's how we know that distance. Here's our first term that we're going to define. It's called H subscript N subscript W. I'm going to write that over here. H subscript N subscript W. And then it's multiplied by C bar, and that's that distance. So N stands for the neutral point of the wing, which is where it's the aerodynamic center or the neutral point of the wing. It's where the lift, the net resultant lift acts. And that's what we were talking about in the configurations. The neutral point is the net resultant force location. So for the wing, this is the net resultant force location. For the wing, that's why we put the W. And notice that it's non-dimensionalized with respect to C bar. In other words, this doesn't have dimensions, and we multiply by C bar. And I'll show you why we do that. So HN wing body is actually the distance X back divided by C bar. Because to get that distance, we have to multiply it by C bar. But we'll always do it in terms of this non-dimensional distance H multiplied by C bar. So if you are doing a problem and you write HN wing equals 5 feet, you're not right. It's just going to be 5, and then you have to multiply by C bar in feet or meters to get the actual distance. Okay, so that's step 2. Draw that thing in. Step 3, let's put the center of gravity. And we're going to just put it at a generic location here. And we're going to locate that with H. So H is the non-dimensional distance to the center of gravity. Multiply by C bar to get it actually in feet. Let me get this out of your way. So let's add that to our list of definitions over here. H is the distance to the CG divided by C bar. So what have we done? We've done step 1, C bar. Step 2 is the neutral point or the aerodynamic center location. And then step 3 is defining where the CG is. Oh, and we need to keep track of this vertical distance as well. We'll call that Z. So the horizontal distance, I know it's weird, but it's H times C bar, but the vertical distance is just called Z. Yeah. Actually, it's the distance from the CG down to where the wing is located. Yeah. With the CG above. It's the same thing. We're just locating everything relative to the CG. Yeah. Step 4. Draw a line through like this. This is called the zero lift line. This is not the chord line. It may be tilted slightly relative to the chord, and maybe I should have done that. In fact, let's do that. Just so tilt it just ever so slightly, like that. So that's the line that if the wind is coming in parallel to that line, you get zero lift. This is what it's called. It's a zero lift line. Okay, so you're doing that. And then draw the actual relative wind coming in. And then this is defined to be the angle of attack of the wing. And the reason we define this zero lift line is then CL of the wing is the lift curve slope of the wing times that angle. Right, because we say if that angle is 0, we don't get any lift, so then it's just the slope times that angle. So are we good so far? Again, we're just defining dimensions and angles and locations. And so now we have to remember which direction does the lift act. I'm going to draw the lift on here. This is step 5. Remember from 324, how do we define lift? Direction. Here's, I guess I need to switch over here real quick. I'm going to switch to the other board. Here's our airfoil. Forget wing for now. Here's our airfoil. Which way does lift act? Is it perpendicular to the chord line? Is it the opposite direction of gravity? What is the definition of lift is perpendicular to V infinity, right? So if the velocity is coming in here, relative wind, then lift is perpendicular to V infinity. And then drag is parallel. And there's nothing magic about that. That's just how everybody agrees to define what lift is. So we go back over here and we're going to draw a lift perpendicular, drag parallel to V infinity. Did you guys on Zoom have enough time to get that other thing drawn? I'll jump back. Everybody good? Got it? So we're going to go back over to the other one and draw that now. So here's lift of the wing. It's perpendicular to V infinity. Drag of the wing is parallel to V infinity. That was step 5. Let's see, step 6. We're good. We already did that. That's defining the lift. Guess I need to write that over here. CL of the wing is the lift curve slope of the wing times alpha of the wing. And sometimes this is called A for the lift curve slope. A moment about the CG, because Newton's law says some of the moments about the center of gravity gives you the rotations, right? So that's for a rigid body from dynamics. So again, I want everybody to draw this picture. I hope you've been doing it as we go along. But this picture, if you draw it, it goes through your fingers, up your arm, because that's the couple. And we're going to calculate the total here. So fix that up. So that's, and I remembered it because now we have to add it in. So that's the pure couple of the distributed aerodynamic load on the wing, which takes a lot of work to figure out because you got all the airfoils spread out all over the wing, and you got to get the distributed load on the airfoils. Then you got to add up all those to get the distributed load on the wing and where it all is located and about the aerodynamic center. So there's a lot of work that goes into that. But we can just write it and we're good, right? Okay. Now, I've got forces here. I've got a vertical component of the lift. Let's draw that in. So there's a vertical component of the lift that way, and a horizontal component of the drag this way, and a vertical component of the drag like that, and a horizontal component of the lift. I'm just breaking those up into directions perpendicular and parallel to the distances that we're going to take with the moment arms, right? That's how you get a moment, is the perpendicular component times the distance, or the lift or the force vector times the perpendicular distance. Can you guys on Zoom see the red? The dotted lines I just drew? Yes, okay. So, what's our first moment? We've got this force going up times this distance. Everybody see that? So we're taking just this component here of the lift times this distance. So it's the lift of the wing times h minus h NW times c bar. So that's the distance out to here minus the distance out to here. And is the plus sign correct? We've defined AC in front of the CG, that's a positive distance. It's up, so that gives a nose up pitching moment, positive, right? Okay, got that one right. Then we've got, let's see, we've got the component of the drag up this way times that same distance. I've drawn it over here, but it's actually acting here, right? So I've got the drag of the wing times that same distance. And what sign do we put on that? Looks like a plus because it's up as well, right? Now I've got the horizontal component of the lift times, and its moment arm is ZW. It's acting down here, right? The component is acting here times that distance, so that's nose up, right? Oh, I forgot to put my signs in here. Hang on. This is lift of the wing What's the component here? Sorry about this. That's cosine. What angle? Yeah, this angle here is alpha because that's how much that tilts over. Sorry, I confused things. Cosine alpha wing. And then that drag component is sine, right? Because we're doing this one. So this is the angle here. And here we got the lift of the wing times the sine of alpha wing. And our moment arm is ZW. Is that positive or negative? Looks like it's down here, acting that way, so it's positive. And then we got the drag of the wing, cosine alpha wing times ZW. And is that positive or negative? We're talking about that vector. It's below the CG, goes down. That's a negative. Let me double check, make sure I didn't get my signs messed up. All right, so that's where we're going to stop for now. Other than to notice, wow, we've just got the wing on the airplane and we've already got a really big giant mess of an equation, don't we? So we're going to start there and talk about, well, what maybe we can do. Are there some approximations we can make next time? Let me check the chat, see if there's anything I can answer real quick before we're done. Everything up to today. Especially the homework. You guys all turn in your homework today, right? So it covers everything up to that homework. It doesn't cover what we just talked about in class today. It covers the homework up to this point. Yes, I typically will provide a formula sheet. You do need to know how to use the formulas. In other words, I won't define all the terms in there, but you need to know how to calculate them. Does that answer the questions about the quiz? And it'll be another 15-minute quiz at the beginning of class on Friday. Oh, a quick announcement. I heard at breakfast this morning from my son that there's a possibility we may get a lot of snow this weekend. It's supposed to be really cold, high wind chills on Monday. So keep a heads up. If things are really bad, I'll shoot out an email and say, I'm just going to do class over Zoom from home. So watch for an email, whether that happens or not. And I'll give you a heads up so you can figure out how early you have to get up or not, whether you can just roll out of bed and turn on your computer. Okay, see you Friday. No, I forgot to look at that. I will look at that right now and shoot an email. Somebody's asking about that there was a difference in the half chord sweep angle from a formula in the book, the handout versus what I gave you. I need to check that out. I apologize. I forgot that.
So she's my TA. Funny how things work out.